Now let us consider another problem where we're going to use the Lagrange's multiplier method to seek the optimum solution. The problem is, construct a tin in the shape of a rectangular prism whose base is twice as thick as the other 5 sides, and we here seek to minimize the material cost for the construction of a tin with prescribed volume V. Let alpha be the material cost per unit area. So then what will be the total cost? So let us refer this diagram. So here we have a tin which is in the rectangular prism form whose base is twice as thick as the other sides, and the dimension of the base will be xy, but if you consider the cost as alpha per unit area, then the material cost will be alpha xy. But since the material cost for the base is twice, as its thickness is twice, will be 2 alpha xy, and for the opposite side it will be just alpha xy. Similarly, the other vertical 4 sides will have the two opposite sides as the same, that is 2 alpha yz, and in the zx plane you will have 2 alpha zx. So let us look at the problem statement. So we are going to minimize the function f, which is nothing but alpha times 2xy plus xy, that gives you 3xy plus 2xz plus 2yz. And what is the condition for the constraints? The condition is, among these 3 variables, your condition will be that you have to have this tin with the prescribed volume V. So volume V is nothing but xyz, and this is the constraint G. So let us again go to the critical points. So at the critical points, the gradients will be parallel. So we have grad of f equal to lambda times grad of g, and this will give rise to this set of 3 equations. When you take the gradients, so equation 1, 2, 3, and the fourth will be the constraint condition. Now we have to solve these 4 equations to find x, y, z and lambda. So we have 4 equations and 4 unknowns, and it is solvable. Now if you look carefully on the right hand side, you have x is missing, here y is missing, here z is missing. So let us try to complete that so that we get on the right hand side v lambda. When I multiply this by x, so you have xyz, that is nothing but the volume, and that gives you lambda times v. And when I bring this alpha this side, what I have is, for all the 3 equations, you have v lambda by alpha equal to the corresponding left hand side terms in the parenthesis, and that gives rise to this sequence of equations. Now if you look at the first 2 here, from this 3xy and 3xy will be equal, and that gives rise to 2xz equal to 2yz, and therefore you get x equal to y from the first sequence of equations. Now let us look at the last 2. Here we have 3xy is equal to 2xz, because the 2yz term cancels. That gives rise to y equal to 2 by 3z. Now equating all the 3 together, we have x equal to y equal to 2 by 3z. Now let us substitute this in 4. That gives us x, y which is x, z which is 3 by 2, x is equal to volume V. That further simplifies to x cube is equal to 2 by 3v, and from here we can find x as 2 by 3 of v and its cube root. Thus, similarly we have y which is nothing but x, and z which is 3 by 2 of x. So we have actually found the dimensions for all x, y, z of the tin in terms of the prescribed volume V. It is also interesting that here we have not sought to find the value of lambda explicitly. which we can do, but for the time it has served our purpose. So once again, here we have got a single option as an answer for the dimensions possible, and that's the solution.